So, the named reaction I chose was the Fries Rearrangement, which was named after German chemist Karl Theophil Fries, who worked with the rearrangement in the early 1900s, publishing the first examples of the reaction in 1908. The reaction is a rearrangement in which the addition of an acid catalyst transforms a phenyl ester group into a hydroxyaryl ketone. A hydroxyaryl ketone is basically a ketone group that's flanked by a hydroxyl group on an aromatic ring, which is why it's aryl. And so this creates a hydroxyaryl ketone group. The rearrangement is ortho, para, selective, meaning it creates both ortho and para groups, depending on the temperature and also whether or not you have other functional groups on the aromatic ring. So let's go through the mechanism. So, basically the rearrangement works by adding some sort of acid to this ester group, and this oxygen takes the acid, creating a positively charged oxygen attached to some sort of acid where the so then what happens is the oxygen attached to the carbonyl group brings an electron pair down, and then this bond breaks and the electron pair goes to the oxygen, which means that the carbonyl group leaves. Now, in this case, because there's no other functional groups, the molecule will create both ortho and para products. So if we have the same, I'm going to write it both. I'm going to go through it twice. Okay. So this means that the carbonyl group leaves, which creates a singular oxygen ether group. So at this point, this is where the mechanism switches depending on if you're creating the ortho or para product, and because this has no other functional groups, it's going to create both the ortho and the para products. So if we have this one, I'm going to go through the ortho product first. The carbonyl that just left will reattach itself. So basically what happens is the pi bond here attaches to the carbonyl carbon, and one of the pi bonds between the carbon and the oxygen moves up, but one of the lone pairs on this oxygen moves down to this bond, which means that the pi bond then leaves and attacks the carbonyl group that has left. So now we have a double bond on the oxygen. This is not a bond, and the acid is still attached. And we now have a new ketone group attached here. Now, oh, and this is positively charged. Now, because this was an aromatic ring, it's going to go through re-aromatization, and it will revert back to an aromatic ring. So basically what happens is the molecule loses a hydrogen. I'm just going to write minus H plus, and the bond comes back. This pi bond moves back up to the oxygen, which is positively charged, and you get the aromatic ring again. So, like this, and there. Now, the last step is to convert the ether group into an alcohol, and we're just going to assume that the solvent is water. So we're just going to add an H2O. The oxygen attacks the hydrogen, the acid leaves, and you get the hydroxy aryl ketone. Yay! Alright, so now I'm going to do it with the para mechanism. It's basically the same with a couple differences. So, first, again, the aromatic ring is going to attack the carbonyl group, except this time it's a little more complicated in that the lone pair from the oxygen moves down, this pi bond moves, and then this pi bond attacks the carbonyl carbon, and then that pi bond moves up. So you get a para functional group. So you have the acid and that. And then the same thing happens. You lose a hydrogen. And it goes boom. They all move. Oh, I forgot the double bond on the oxygen. And then this goes back up to the oxygen, which was positively charged. And you get the re-aromatization. It's an aromatic ring again. And then again, you have H2O, and the ether is going to switch back into an alcohol. And you get the para rearrangement. Ooh, I ran out of space. The para rearrangement. So these are the two molecules that you get. You can manipulate the product based on temperature or by adding a functional group onto the ring. So, for example, here we have a aromatic ring with the ester group, and then R. This is R. And then I added a bromine. So that means when you add an acid like AlCl3, you're going to have the ortho rearrangement because you can't have the para rearrangement. So the Fries rearrangement can also be induced through photochemical excitation. So when you add light instead of an acid, you get the same sort of reaction, but just induced by light. So you have the ester group with light, it breaks off, attacks the carbonyl, rearomatization, and you have the ortho and para groups. And it's basically the same thing. So yeah, that was the Fries rearrangement. Yay!